Welcome back to the deep dive. Let's jump right in. Have you ever looked at text on your computer, phone screen, letters, symbols, even emojis, and just wondered how the machine actually understands and displays it? I mean, computers only really get at E's and ones, right?
hmm
Binary. So how do we possibly bridge that gap between just simple binary code and this incredibly rich, like, tapestry of characters we use from languages all over the world? Today, we're taking a deep dive into exactly that. We're going to unpack the whole story of character encoding, which is basically how computers learn to read and write human language. Our source material for this is Hello Algo, which is a fantastic resource. Really helps break down these fundamental building blocks of computing.
That's exactly right. And our mission today, you could say, is to really trace that journey. We'll look at how we started with pretty limited ways to represent text, then how things got kind of chaotic as computing went global, and eventually how we landed on the, well, pretty elegant universal standards that power text everywhere today. And understanding this stuff, it's not just academic. It's key to figuring out why you sometimes see that garbled text, or how different languages get handled, and even how the actual strings you might work with in code behave under the hood. We're aiming for a really detailed look today, something that helps you properly grasp and hopefully remember this core concept.
Okay, let's unpack this then. What's the very first, like, the rock bottom fundamental challenge here? We want computers built on binary to handle characters like A or B or maybe a question mark.
Yeah, the absolute core problem is taking something symbolic, something meaningful to us humans, a character, and representing it using only those zeros and ones that computers understand. Because everything in a computer, all data, is ultimately stored as binary. So characters are no different. We need a system, a consistent rule book. This system maps each character we care about to a unique sequence of bits. And that mapping, that rule book, that's what we call a character set. Think of it like a shared dictionary, or maybe a code book. When the computer needs to show an A, it looks up the binary sequence for A in its character set and, draws the shape. When you hit the A key, it consults the set to find the binary sequence it needs to store or send. Without that shared map, a sequence of bits is just, well, it's just noise. It doesn't mean anything as text.
Right. And I guess back in the really early days of computing, that code book, that character set was probably pretty simple because the needs were, well, simpler. Which brings us to ASCII, right? What was ASCII all about?
Yes, exactly. ASCII, that stands for the American Standard Code for Information Interchange, was really one of the foundational character sets. It's designed mostly for English and basic computer control stuff. It used a pretty small number of bits, just 7 binary digits, which fit nicely into the lower part of a byte, an 8-bit unit. So 7 bits means ASCII could represent, let's see, 2 to the power of 7, 128 different characters, max.
Okay, 128. What did that actually include?
It had your uppercase and lowercase English alphabet, A to Z, the numbers 0 through 9, standard punctuation periods, commas, question marks, that sort of thing, and symbols like the $sign or ampersand. Plus, importantly, it also included some non-printable control characters, things like new line or tab that were needed for old teletypes and terminals. ASCII was super important. It gave a common standard for basic text, but, and this is the key limitation, as the name suggests and the source points out, is really designed for English characters only. It had no room, no way to represent characters needed for, well, pretty much any other language.
Ah, okay. So naturally, as computers started spreading outside the US and UK, that limitation must have become a massive headache pretty quickly. We needed more characters, which led to ESCII extended, ASCII.
Exactly right. To try and cope with other Western European languages, with accented letters like A or U or extra symbols, developers extended the ASCII idea. ESCII or extended ASCII versions, really they basically used the full 8 bits of a byte. ASCII only used 7 bits, leaving the highest bit as 0. ESCII used that 8th bit. This doubled the capacity, right, from 128 characters up to 2 to the power of 8, so 256 characters. And crucially, the first 128 characters in any ES-cap were always the same as standard ASCII for compatibility.
Okay, 256 sounds better, but you said versions. Did that cause problems?
Oh, did it ever. That's where things got really messy. Because unlike those first 128 standard ASCII characters, the second 128 characters, the ones using that 8th bit, they were not standardized globally. Not at all. Different companies, different regions, they defined those upper 128 characters totally differently. So you might have one ASCII set, maybe called Latin 1, for French, German, Spanish characters, then another one for, say, Greek characters, and another for Cyrillic used in Russian. They all use the same numbers, 128, 255, but mapped them to completely different characters.
Ah, I see. So incompatibility nightmares.
Total incompatibility nightmare. If you typed up a document using, say, a French ASCII setup and sent it to someone whose computer was using a German ASCII setup, well, those characters in the upper range, numbers 128 to 255, they'd be interpreted using the wrong lookup table. So instead of seeing the French S, they might see some random German symbol or maybe just gibberish. This was a super common reason for that awful garbled text we all used to see when swapping files.
Right, I remember that. Moji bake, some people called it. And even with 256 characters, ASCII was still way too small for languages with huge character sets, like you mentioned Chinese earlier, thousands and thousands of characters.
Precisely. 256 is nothing when you're dealing with Chinese, Japanese, or Korean scripts. ASCII couldn't even scratch the surface. So this forced the creation of entirely separate language-specific character sets and encoding standards. The source uses GBK as a key example. It built on an earlier standard, GB-312, and was developed specifically in China to handle Chinese characters. GBK was a huge leap in scope. It included 21,886 Chinese characters, way beyond ASCII's, and to manage this, GBK used a clever trick. A variable length encoding, your standard ASCII characters. They still use just 1 byte, same as always, but those thousands of Chinese characters, they each required 2 bytes to represent.
Okay, now this is where it sounds like it gets really complicated globally. We've got ASCII for basic English, a whole mess of conflicting ASCII versions for European languages, then totally separate multi-byte sets like GBK for Chinese, and I'm guessing similar things for Japanese, Korean, Arabic, Hebrew. What did this fragmented world look like in practice?
Chaos. Honestly, it's chaos. The problems just piled up. First, like you said, these sets were built for specific languages or regions. So creating a single document or web page that correctly displayed text from, say, English, French, and Chinese simultaneously. Hugely difficult, often impossible. Multilingual computing was a real headache. And second, that garbled text issue we talked about, it became rampant. If you got an email or loaded a web page or opened a file and it was encoded using, say, GBK, but your system thought it was supposed to be, I don't know, some ASCII variant like Latin 1, well, those 2 bytes, meant to be 1 Chinese character in GBK, would get interpreted as 2 separate meaningless characters according to the Latin 1 map. Utter gibberish. Sharing information reliably across different languages and different computer systems was just incredibly difficult. It screamed out for a unified approach.
You can just picture researchers banging their heads on their desks thinking, this is insane, there has to be a better way. Instead of juggling dozens of incompatible codebooks, what if? What if there was one single enormous codebook? One that contained every character, every symbol, every script from everywhere in the world.
Exactly. That's the grand, ambitious idea that led to Unicode.
The breakthrough moment.
Pretty much. Unicode is the direct answer to all that fragmentation. The name itself, Unified Code, spells out its mission.
Yeah.
Gather characters from, well, basically all writing systems. We're talking historical scripts, modern languages, math symbols, technical symbols, punctuation, and yes, every single emoji you use on your phone, all into one single consistent character set. The explicit goal was to kill off those problems of language-specific sets and finally put an end to garbled text by providing one universal standard everyone could use.
Okay, so how does it work? Does everything just get a number?
Essentially, yes. Within the massive Unicode standard, every single character gets assigned a unique identifier, a number. That number is officially called a code point. So A gets a code point. A gets a different code point. The Chinese character for water gets its own code point. The pile of poo emoji, yep, it has its own unique code point too. These are just abstract numbers, though. They aren't tied to a specific binary representation yet. Unicode itself is designed theoretically to handle over 1 million possible characters. As of the source's data from late 2022, it already defined 149,186 characters, covering just a huge range of languages, scripts, soundles, everything.
Wow, nearly 150,000.
And growing. Now, here's a really crucial point, something that often trips people up. While Unicode assigns that code point number to each character, the Unicode standard itself does not specify how computers should actually store those numbers as binary data, as zeros and ones, or how they should send them over a network.
Ah, okay. So Unicode is the giant universal list of characters and their numbers, but not the method for writing those numbers down in binary.
Exactly. Unicode is the map, the dictionary. It doesn't define the binary format. And this naturally created a new challenge. How do you take these code point numbers, some small, some potentially very large, and represent them efficiently and, importantly, unambiguously using bytes? especially when characters might need different amounts of data. How does the system read a stream of bytes and know where one character's binary code ends and the next one starts? That became the next big problem to solve.
Right, because you could just say, okay, the biggest possible Unicode number needs maybe 4 bytes to represent it, so let's just make every character take up exactly 4 bytes, pad the smaller ones with zeros or something. But what's the obvious downside there?
Yeah, the immediate and really significant drawback is massive inefficiency, especially with storage space and memory usage. Remember ASCII? Those basic English letters, numbers, punctuation, they only need 1 byte each. If you suddenly force every character, including all that common ASCII stuff, to occupy a fixed 4 bytes, you've just quadrupled the storage space needed compared to old ASCII text. Even if you pick the fixed 2 bytes, you're still doubling the space for ASCII. That's incredibly wasteful, especially when you consider how much text data in the world is primarily English or heavily uses ASCII characters. It just bloats everything.
Makes sense. So a fixed length solution is simple but wasteful.
Precisely. And this is the exact problem that UTF-8 was brilliantly designed to solve. It's why UTF-8 has become, by far, the most dominant and widely used way to encode Unicode text internationally. Its core genius is that it's a variable length encoding. It doesn't waste space by using a fixed number of bytes for every single character.
Okay, variable length, how does that work in practice?
UTF-8 cleverly uses between 1 and 4 bytes to represent a single Unicode character's code point. It adapts, using more bytes only when needed for characters with larger code point numbers. And here's the really clever part. Characters that correspond to the original 128 ASCII characters, the ones with the smallest code points, they are represented using just 1 byte in UTF-8.
Ah, so it matches ASCII for the basic stuff.
Exactly. And that single byte is identical to the original ASCII encoding. This means UTF-8 is fully backward compatible with ASCII. Any text file, any data stream that was pure ASCII, it's also perfectly valid UTF-8. You can open an old ASCII file in a modern program that expects UTF-8, and it just works. No conversion needed. It's a huge compatibility win.
That's really smart. Okay, so 1 byte for ASCII. What about other characters?
Right. For characters with slightly larger code points, think most Latin characters with accents like in French or German, or characters from Greek, Cyrillic scripts UTF-8 typically uses 2 bytes. Then, for the vast majority of commonly used characters in East Asian languages, Chinese, Japanese, Korean, plus many symbols, it uses 3 bytes. And finally, for the rest, very rare characters, ancient scripts, some less common emojis, characters with the largest code points, UTF-8 uses 4 bytes.
Okay, 1 to 4 bytes. But how does the computer know if it's seeing one 1-byte character, or the start of a 2-byte sequence, or maybe the middle of a 4-byte sequence? How does it keep track?
That's the other really clever part. The encoding rules themselves have markers built in. For a 1-byte character, which is just ASCII, the first bit of the byte is always 0. The remaining 7 bits are the code point, just like original ASCII. Now, for any character that needs more than 1 byte, let's say it needs n bytes, where n is 2, 3, or 4, the very first byte tells you how many bytes are in the sequence. It starts with n ones, followed by a 0. So a 2-byte character starts with 110. A 3-byte character starts with 1110. A 4-byte character starts with 1110. Then, crucially, every following byte in that multi-byte sequence, the second, third, or fourth byte always starts with a specific bit pattern 10. The remaining 6 bits in those continuation bytes, along with the bits of the first byte after the marker, all combine to hold the actual code point value.
Wait, why that specific 10 pattern at the start of those continuation bytes? What does that achieve? Why is that important?
Yeah, that 10 is actually super important. It's like a flag or a marker that provides robustness when reading the byte stream. Imagine a program starts reading bytes somewhere in the middle of a file or network stream. If the first byte it sees starts with 10, it knows immediately, hold on, this cannot be the start of a new character. Why? Because only continuation bytes begin with 10. The start bytes always begin with 0 or 110 or 1110 or 1110. So seeing that 10 tells the system it's landed mid-character. It can then just scan forward byte by byte until it finds a byte that doesn't start with 10. That byte must be the beginning of the next character, allowing the system to resynchronize and start parsing correctly from there.
Ah, clever. So it prevents misinterpreting the middle part of one character as the start of a new one.
Exactly. As the source material proves, based on these rules, no valid character can ever start with a byte beginning 10. It's a simple but really effective way to make parsing these variable-length sequences reliable, even if you encounter errors or start reading at an arbitrary point.
Okay, so summing up UTF-8, it's variable length using 1 to 4 bytes. It's backward compatible with ASCII, which is huge. It's space efficient, especially for text that's mostly ASCII or mixed. and it has this built-in way to figure out character boundaries reliably.
You got it. That combination makes it incredibly flexible and practical. It really hits a sweet spot between supporting everything in Unicode and not wasting tons of space. It's no surprise it became the de facto standard for the web, for email, for pretty much all modern text file storage.
Makes total sense. Now, are there other ways to encode Unicode that are still around? You mentioned UTF-8 is dominant, but not the only one?
Yeah, while UTF-8 is king, the source does quickly mention a couple of others you might encounter, especially in certain programming environments or older systems. One is UTF-16. This one mostly uses 2 bytes, 16 bits per character. A lot of common characters, including ASCII and many widely used non-English ones, fit into those 2 bytes. And for many of those 2-byte characters, the UTF-16 binary representation is just the same number as the Unicode code point, which can be convenient sometimes. But, just like we discussed with fixed-length ideas, Unicode eventually outgrew 16 bits. So for characters with code points needing more than 16 bits, UTF-16 has to use a workaround called surrogate pairs. It uses 2 16-bit units together to represent one of those larger code point characters. So characters in UTF-16 can be either 2 bytes or 4 bytes long.
Okay, so UTF-16 isn't strictly fixed length either because of those surrogate pairs.
Exactly. And then there's UTF-32. This one is simple conceptually. Every single Unicode character, no exceptions, is represented using a fixed 4 bytes, 32 bits. The advantage is uniformity. Every character is exactly 4 bytes wide. Makes indexing seem easy. But the big downside, as we already covered, is space. UTF-32 is often very inefficient, especially for text with lots of ASCII, using way more storage and memory than UTF-8 or even UTF-16 usually would.
So, quick comparison then.
Sure. For storage space, UTF-8 is generally the most efficient, especially if you have lots of English ASCII text. UTF-16 might be slightly better than UTF-8 for some specific languages where most characters need 2 bytes in UTF-16, but would need 3 in UTF-8, but that's less common overall. UTF-32 uses the most space, period. For compatibility and just general use out there in the world, UTF-8 is the clear winner. It's supported pretty much everywhere.
Got it. Okay, that paints a really clear picture of how text gets stored in files or sent over networks, usually UTF-8. But let's shift gears slightly. Inside a program, while it's running, how do programming languages actually handle strings and characters in memory? Do they all just use UTF-8 internally too?
That's where things get interesting again. Historically, and actually still today in some major languages, the answer is often no. Many languages, particularly those developed a bit earlier, actually chose to use fixed-length encodings like UTF-16 or sometimes even UTF-32 for their internal representation of strings in memory.
Why would they do that if UTF-8 is so good for storage?
There were some pretty compelling reasons back then, mostly related to performance and maybe perceived simplicity for certain string operations. A big potential advantage of fixed-length internal storage is random access. If you know every character is, say, exactly 2 bytes wide internally, and you want to jump straight to the 500th character in a long string, easy calculation, start address, plus 499 times 2 bytes, boom, you're there. It's super fast, what computer scientists call O1 or constant time. Counting the number of characters also seems simple. Just divide the total byte length by the fixed size per character. Again, O1. With a variable length encoding like UTF-8 inside your string. To find the 500th character, you usually have to start at the beginning and step through byte by byte, figuring out where each character ends until you've counted 500. That takes time proportional to the position you're seeking O1, which can be noticeably slower for very long strings or frequent random access. Also, operations like splitting strings or getting substrings could seem simpler if you're always dealing with fixed-size units.
Okay, so performance for things like jumping to a specific character index. Which languages went this route?
Well, the source points out some big ones. Java's main string type, for example, historically used UTF-16 internally. This decision was heavily influenced by the thinking at the time Java was created, when many thought 16 bits would be enough for all of Unicode. JavaScript and TypeScript also predominantly use UTF-16 internally for strings. Again, partly historical reasons tied to when JavaScript originated in browser implementations. C# also went with UTF-16, aligning with the .NET platform in Windows, which used UTF-16 extensively.
Right, but you mentioned earlier that Unicode outgrew 16 bits. How did these languages cope when they needed to represent characters that didn't fit in 2 bytes?
Yeah, that became a bit of a snag. They had to introduce those surrogate pairs we talked about. So a character needing more than 16 bits gets stored internally as 2 consecutive 16-bit units that, together, represent the single larger code point. This kind of complicated things. The internal representation wasn't truly fixed length anymore. Some characters, from a user perspective, took 2 bytes, others took 4 bytes, the surrogate pair.
This undermines some of the original performance benefits of fixed length, like simple indexing or counting. Developers suddenly had to be careful with string.length, counting 16-bit units or actual user-perceived characters. It added a layer of complexity.
Yeah, sounds tricky. So given those challenges with UTF-16 and surrogate pairs, did other languages try different approaches internally?
They did. Different languages adopted different strategies, trying to find a good balance. Python, for example, has a really interesting approach for its standard strike type. It uses a flexible internal representation. The actual storage size per character 1, 2, or 4 bytes isn't fixed globally for all strings. Instead, it's chosen dynamically for each individual string based on the largest Unicode code point found within that specific string.
Oh, that's clever.
Yeah. So if you have a Python string that only contains ASCII characters, Python will store it internally using just 1 byte per character. Super efficient. If the string contains characters that need up to 16 bits, but nothing larger, it uses 2 bytes per character for that whole string. If it contains even one character needing more than 16 bits, like a rare emoji, then the entire string gets stored internally using 4 bytes per character. It adapts to the content.
And what about other more recent languages?
Languages like Go and Rust took a different path again. They decided to embrace UTF-8 for their primary internal string types: string in Go, straw in string in Rust.
Yeah.
Since UTF-8 is variable length, accessing the nth character is an O1, but they provide good libraries for working with UTF-8 efficiently. And importantly, they also provide separate, distinct types. Go has rune, Rust has char, that specifically represent a single Unicode code point, which can be 1 to 4 bytes in the UTF-8 string. This lets you iterate or work with individual code points clearly when you need to, separating the concept of a byte from the concept of a character.
Okay, so lots of different internal strategies, but the key distinction is still.
Yeah, the really key takeaway the source emphasizes is distinguishing between these internal memory representations chosen by a programming language, often for performance or historical reasons, and the encoding used when data goes external. When programs save strings to files, send them over networks, store them in databases, basically. Anytime text leaves the program's internal memory, the encoding used is overwhelmingly likely to be UTF-8 because for interoperability, space efficiency, and the ability to handle the entire Unicode range, UTF-8 is generally the best choice for data exchange in the real world.
Wow. Okay, that was quite a journey. Oh, we went from the super basic English-only ASCII through that messy period of conflicting e-size and separate language sets like GBK causing all that garbled text.
Yeah, the wild west of encoding.
It's like a big unifying idea of Unicode, giving every character its own number, its own code point.
The universal dictionary.
Right. And then the really clever engineering behind how to encode those Unicode numbers efficiently, especially with UTF-8, using that variable 1 to 4 byte approach, being ASCII compatible, and having those smart 10 markers for robustness.
Absolutely. Solving a storage and parsing problem elegantly.
And finally, diving into how programming languages grapple with this internally, the trade-offs between fixed length like UTF-16 with its surrogate pair issues, and flexible or UTF-8 internal models like Python, Go, and Rust use.
Exactly. It really shows the evolution and the different priorities, internal processing speed versus external compatibility and efficiency. Understanding that whole path, from ASCII to UTF-8 and internal choices, really helps make sense of why text just works most of the time across different systems and languages today. And it definitely explains those frustrating moments when it doesn't work, when you see that garbled text.
Absolutely. It's fundamental stuff. So, to leave everyone with a final thought from this deep dive, think about that UTF-8 backward compatibility with ASCII again. We mentioned you can just read old ASCII files with modern UTF-8 tools. Now consider the absolutely massive amount of plain text data created back in the decades before Unicode and UTF-8 really took over. Old source code, email archives, simple text documents, scientific data, just tons of stuff stored as basic ASCII. How incredibly important, how profound was that single design decision in UTF-8 to represent ASCII characters using the exact same single byte as original ASCII? How much easier has that simple choice made it for us today to access, read, use, and preserve that gigantic digital history without needing complex, potentially lossy conversions everywhere? It's a really subtle but powerful design choice connecting computing's past right through to its present. Something to chew on.